So you know by now, atoms can stick together. We haven't gotten into bonding, that's in a little bit, but you know that you have things such as formulas, where we stick these atoms together and the little number down here tells us how many that there are. So there's something really important related to these numbers, and it has to do with their ratios. If you'll notice, the ratio of this number to this number to this number, it's a ratio of 6 to 12 to 6, which is the same thing as saying 1 to 2 to 1. Now we have instruments that can tell us the ratio of the atoms, like it can tell us the mass ratio of the different atoms, but it can't tell us whether it's a 1 to 2 to 1, a 6 to 12 to 6. It can't tell us that information. We have to get it in another way. But these instruments are very, very readily available, and we use them a lot. So we need to explain the difference between an empirical formula, which is actually this form, and a molecular form, which is anything else with that ratio where it's not the lowest numbers. So you'll notice right here, we have something and it's C6H12O6. That's glucose. So we love to eat glucose. You know, it's sweet and it's yummy. So this has different properties than this compound that's below it. This is acetic acid, which is the same thing as vinegar. You'll notice that it is, edible depending on your palate. But the vinegar we eat is 5% vinegar and the rest of it's water. And so if we're talking 100% vinegar, that might be a little bit different. You'll notice the ratio, though. This is 2 to 4 to 2, which, I'm sure you can see, is a 1 to 2 to 1 ratio, which was the same ratio that this one was. It was a 1 to 2 to 1 ratio. However, because these atoms right here aren't the lowest ratio, we still aren't at the empirical formula. You have to go all the way down to here, and now you can see that there's no way to simplify this any further. These are understood ones, and then that's 2 to 1. So the empirical formula, the only way that you get to the empirical formula is by having the simplest ratio. And so in this case, it would be CH2O. Everything else in here can be simplified down to CH2O, but it isn't. It's a different kind of a formula. O6. And by the way, this is formaldehyde, which is it's a preservative. It's the type of preservative that you smell when you're opening up something to dissect it. It is obviously not good for you to eat. It is very poisonous. So just because they have the same ratio, it does not mean that they have the same properties or that they look the same or anything. It's just that we have equipment that can give us that ratio. So comparatively, that would be an example of a molecular formula that would match up. Now, if we wanted one more example, and it doesn't always have to be carbon, hydrogen, oxygens, it can be other atoms, but it's almost some of the easiest ways to write empirical versus molecular is with carbons, hydrogens, and oxygens. So you'll often see it. So if I took N2O4, you'll notice that that's not the simplest ratio. So that would go in this category. It's not the simplest ratio. The simplest ratio would be NO, and that would be an understood 1, and there's a 2 there. So that would give us our 1 to 2 formula. So again, to be empirical, that's the simplest ratio. I like to think of this as the easy one. Like they always look a lot easier when you read them because they don't have as many numbers in it. And then this one, it's where you come up with a multiple of the easy ones. So this is like a multiple. That's like multiplying everything times 6. And this is like multiplying everything times 2. And then over here, this is like multiplying that one times 2. And if you want to try to come up with another one, and it may or may not exist, but you could jump this all the way up to N10O20, and you could call that a molecular formula. It just may not actually really exist. So that's the difference between empirical formulas and molecular formulas.